Okay, here we are for today. There's a quiz due today, and it's attendance based. If you're here, you get credit, and I've just written down a list of everybody who's here, so you don't need to turn anything in. Those of you watching on video will be seeing this a little bit too late, I guess, but you still have the option of turning it in by the end of class electronically, if that's the route that you want to use. All right, finishing up the review for the exam. Is the exam on everybody's radar for Wednesday? Okay. The weather will be not as nice then, so you will not feel you won't feel as bad about being inside then. At least that's what I'm hoping. Okay, so let's finish up where we left off last time. We were in the middle of the quiz 5 portion, and here's just a little chance to do a bounce back and review some lipid material. 4 was all about carbohydrates, 5 is about lipids. So here we are again. Do you recognize all of these as lipids? Okay, that's one thing to notice. And what do they, because they're all lipids, what do they all have in common? What? Let's see, a strong base would affect these right here. But lipids are defined as a group, not by any functional group. Okay, so one step back. Carbohydrates are what? Polyhydroxy, they're functional groups. Aldehydes and ketones, right? Lipids, look at all these different functional groups on here. There is no one functional group that tags something as a lipid. So what would you say does tie them all together? It's solubility. And what are they soluble in? Nonpolar solvents. Yeah. Okay, so there's a set of 4 of them, and since we're reviewing, I'm going to add one more. The wax is just a long ester, so something like this. You don't need to count carbons, just draw a bunch of them. Earwax. Wax in your ears looks like that, long tails on the ester. Okay, so let's look at all these together and come up with a way to describe each one, and then use that little review to go into questions 2 and 3, which would be formatted multiple choice on an exam. Okay, so take a look at the first 2, maybe as a group, and these are certainly glycerol esters, but they are diesters. And they have a charged so-called head, and they have a long tail. All right, that's what the first 2 have in common. The next one, could you look at the next one, which is part C? Could you put a name on it or say anything about where it is? Yeah, that one's a triacylglycerol. There it is. That's in your diet. The next one, what kind of general term do you put on D? It's a lipid for sure, but what kind of lipid? Steroid. Yeah, that one's a steroid. This one happens to be cholesterol. Okay, and then part E, there's wax. And that's most of your lipids all in one frame right there. Okay, so the question is for number 2, which one is not likely to be a component of a cell membrane? And because I've added a choice here, there may be more than one right answer. Well, I suppose the way you do this is look at it and figure out which ones could be a component of a cell membrane. And how about we tag these over here? Both of these hang out in membranes. Those are really the structure of a cell membrane. and so is this. Cholesterol is not all bad. You definitely need some of it in your cell membranes to stiffen them up. And that would then just leave C and E. To fit into a membrane, it needs to have some part of it that's charged or polar or something, so it can face the outside or the inside. There, yeah. So that's a little review of all of them at once. And then the next one, which one is a triacylglycerol that's likely to be a solid at room temperature? Well, definitely C. And why is that? And there's a reason here. Because it is, and then there's a dietary term that goes after that. Yep. No double bonds. Okay, then moving from there to cell membranes in general is where we get when you go to number 4. So what kind of protein, what's the term here, is it that goes not just on the surface, inside or outside of the cell, but it goes all the way through? Yep. There are enzymes that catalyze reactions on the outside and then talk to the inside, so they need to be integral. Poke all the way through. Okay, so here's the next question. This will entail just some knowledge of this, and here's the difference. This is prime, and this is not prime. So how are they different? Okay, anybody have, let's make a list here. There's more than one right answer, but you need one of these. So how is the prime one different?
You can use at any temperature.
It's a different temperature. Prime, so let me write that in parentheses here. Delta G0 prime is something that works at, and then there's one temperature, which is not the standard temperature, 25. Yeah. Okay, and then there's one other difference here, which is, again, the prime version, delta G0 prime, is also different from the standard one without the prime. What's another difference? Yeah. If you had a proton concentration of 1 molar, no cell in your body could withstand that. So those are the big differences, and the prime one, that's the one that gets quoted in your metabolic reactions, which we will come to see more of later. All right, on that page, is there anything else? All right, I guess that gets us down to the last page. So 6 is true or false. A reaction with a higher equilibrium constant must be faster than a reaction with a smaller equilibrium constant. Now, remember, KEQ is your concentration of products over reactants. And it's, I guess I'll also, that's too messy. KEQ is related to delta G0 prime. Okay, but this question is about speed. And the question is there such a relationship? Can you say that a bigger equilibrium constant means a faster reaction? No, never. The fact that you have a big equilibrium constant may just mean that you have an even bigger hill in the middle, right? That would be a big KEQ. It's a big minus delta G. There's more than one way to say that, but it's slow. I know that's cramming a lot in one space. I'm assuming that this is a little bit of review for you, so if you don't need that, that's okay. Big hump in the middle means slow. Okay, so the next one is one that usually confuses at least one person, so let's kind of go through it. 7 and 8 both refer to this one reaction here. So here's to start out with an aldehyde, 3 carbons, and by the time you're over to here in the product, it has been reduced. There it is. And there's something else here. This reactant turns into this product. It's not balanced, but we're not going to worry about that. So let's do 2 different mappings here. One of them will track, this would be the fuel molecule, and then this one right here is this. Okay, your first one, the aldehyde. What happens to it? Does it get reduced or oxidized? Reduced is right. And why do you say that? Yep. Okay, as of right here, this one has fewer CO bonds and it has more CH. If you counted on that one carbon, you'd see the CO count go down by 1 and the CH count go up by 1. Okay, then you're looking at the other piece of it right here, and here's one of our common biological reactants that we're recognizing as an abbreviation. In this form right here, it's NADH. By the time you get over here, it's not just missing an H, it's actually positively charged. It must have had something removed. It loses H, not just H, but H minus. What do you call that then? Reduction or oxidation? You're losing a hydrogen, H minus. Anybody want to try it? That is a... Yep. Now, it would be fair to write this reaction backwards. It's known to happen both ways. So if you were starting with this side over here, going to this one, you'd have to say that this is a reduction. The opposite is a reduction. Whereas for the organic piece of it, you'd say it's an oxidation. It's fair to write it either direction. And it does happen either direction. By the way, this is for a 3-carbon alcohol. But if it were a 2-carbon alcohol, you'd be looking at the first step in detoxifying ethanol. So, you drink a little too much and build this up. Your body's mechanism is oxidize it by running the reaction this direction. Okay, so the aldehyde gets, just to finish this in the right spot, in the right blank, aldehyde gets reduced. And the reaction is probably an example of, what do you say? Should be anabolism or catabolism? Anabolism, remember, is something that tends to reduce little molecules and head them maybe towards bigger assemblages. So this is probably anabolism. Okay, and let's make sure you get the reason in, because it reduces a small molecule, that's the little 3-carbon one, because it oxidizes NADH. Okay, this one, I forget. Was this actually on your quiz? Okay, I think that's where the quiz questions ended, so we can end right there as well. But I included these right here just as a way to hit the review portion, even though it wasn't part of the quiz. Make sure you know these and know these. There will be some exam questions based on that part of the notes. There were, I don't know, a list or a table format or whatever it was. There'll be a question or two taken out of that as well. For the most part there, what you're looking at between these two quizzes is the bulk of the exam. That's the way it's intended, the way it should be. Looking at all of that then put together, where all have we been? Those two quizzes, reformatted as exam. Do you have any questions about any of it? Are you okay with recognizing different molecules, drawing them, if need be, using the right descriptions? Yeah, Ariana.
I have a question about like the first of the quiz 5 first question.
Okay.
I'm confused about when you have omega-3 fatty acid, is that where the double bond starts?
Yes, let me try to find that one.
Of course, yes.
Oh, here we go. Okay, so let me add something to that then. So it would be abbreviated like this. Fatty acid. Okay, start off from, I'm going to draw this from left to right. So you go 1 and 2, there's omega, there's omega 1, here's omega 2, here's omega 3, here's omega 4. That's where your double bond starts, right there. So it will, by definition, go from omega 3 to omega 4. And then you've got the rest of the molecule. Now, because this was described as a fatty acid, you need to end it in a carboxylate group like that. But the important part is omega, omega 1, omega 2, omega 3.
So we always start from like the omega end, right, when counting?
Yes. You start from the end that is not the carbonyl group. Now, this is the opposite of what you learned in your organic course. It's very chemical. The biological language tends to focus on other parts of the structure, and so you kind of got to deal with both. So yeah, numbering would be from this end. That would be 1, 2, 3, and 4, but not omega. Omega means you go from this end. Okay, one more chance to emphasize this. That's cis, right? That's all the natural ones. If you see it trans, that means it's been through an artificial process. The manufacturer is trying to add hydrogen. The catalyst made a mistake and left you with something that's kind of a nutritional headache. Okay, anything else?
Just have one more question for question 2. So I put,
Same quiz?
yes, I put A as like not likely to be able to like some memory because its overall charge is negative. So the way I thought of it is that it wouldn't fit into like a neutral cell membrane.
Yeah. So it actually can fit because on the inside and the outside there will be plenty of cations to balance it out. You're probably right, there probably is more of this in a cell membrane, but anything that has this structure of a polar head will do okay in a membrane. Let's see, this one right here, trying to think of how you encounter that one nutritionally. It's before it picks up the ester with the amine group on it. I can't quote a dietary source. Anybody seen lecithin used as an ingredient? It's good. Yeah. Lecithin is one of these. I think it's this one right here. Phosphatidyl so-called ethanolamine. And you use it when you want to tie together a fatty component with a water component. So I could tell you about my experiments of making candy, trying to make candy. You all know that if you take a sugar water solution and heat it long enough, it'll get thicker and thicker and thicker. Okay, so I forget what fat I wanted to mix that with. It may have even been something as silly as peanut butter. But anyway, I mixed those two together and tried to add some lecithin to make them compatible, but my mistake was heating too long. Okay, I ended up caramelizing the sugar, and I had to clean that pan out with a wire wheel on a drill, just to let you know how that one ended. Not all my cooking experiments go that badly. Okay, what other questions do you have here? Anything else you want to review? No, those of you who are here, I have your names down. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Got you all. Okay, then let's call it done on a day when it's good to go out early, huh?